Lesson 2 is about the choice of model. As it says, sometimes, like we did in the first lesson, just testing the explanatory power of a model it isn't really possible. We might have a theory, might not be able to say, I think for each year you get older, you'll increase your height by the same amount. We might just have some data that we've collected and have no idea about the relationship between the two variables. Okay, so in this case, it's useful to plot the data and choose a model which may explain the data. Okay, so typically you'll have a few models in mind and then test how well the data fits the model using the R-squared. All right, so just so that you know all the family of functions that are out there, okay, we've got a linear model. So these models, I should create my own stuff. I stole this online. A linear model, y equals mx plus c. Quadratic model, ax squared plus bx plus c. Cubic model, x cubed plus bx squared plus cx plus d. Exponential model, probably write this as k a to the power x. Square root model, okay, we still need a constant out the front. Same thing for the cube root model. And logarithmic and reciprocal, that should be a on x plus c, just for the complete generality. Alright, so these are our complete suite of models. Okay, so linear, straight line. Quadratic has this thing called a turning point. Cubic has this point called a point of inflection. We'll study them a lot more in the future. Exponential should be able to tell me this one. No? Okay, I'll tell you. Has the horizontal asymptote. Square root function, okay, has an endpoint here. Okay, you might see there's some relationship between these two. Okay, the square root function, this part we have here is just this half of a quadratic on its side. Cube root function, okay, so square root, obviously put in any negative x value into your square root, you won't get any y value. That's why there's nothing on this side, why the domain's restricted. In cubed root, that's not the same. So I can have, I can find the cubed root of 8. Okay, I know that's minus 2, since minus 2 times minus 2 times minus 2 gives me 8. Yeah, that's why the cubed root model is there here as well. Logarithmic, there's some dashes on here. Yep, so it's got a vertical asymptote. And reciprocal has the vertical and horizontal asymptotes. Okay, so they're the models that we're going to choose from. And you'd have different reasons for all of these. Like, imagine if I had if I had some cubic data. It seems to fit a cubic model, okay. I go to my calculator, I fit the cubic model. It gives me something like this. Okay, show some more data out here. I might say, okay, cubic model seems okay for the data, but for this x equals a half, it gives it predicts a negative value, which may not be appropriate. So the shape of the graph is sometimes a big consideration. Okay, so I think the easiest way is to look at some data. Okay, we've got some data about Vehicular stopping distances, so how fast you go, okay, in miles per hour versus stopping distance in feet. And we want to analyze this data. So the first thing I'll do is put it into my calculator. I've already done that. That's the magic of television. And graph it. Just make sure I set my graph properly. Yep, looks good. Graphy. There we go. I'd look at my data, and I'm going to choose one of these models. Okay, by the look of it, I'm going to be choosing one of these three: quadratic, cubic, or exponential. Okay, so for part A, I'll choose quadratic, cubic, or exponential. Okay, as the stopping distance increases with speed, but faster than a linear model. And we can see that in our data as well. This increase of 5 here led to an increase of 14, whereas this increase of 5, okay, led to an increase of like 44.5, 43.5. Okay, a much bigger increase. Is that even right? Wow, doesn't matter. Okay, so looking at data, let's have a look. I'm going to draw lines of best fit through these. So I'll try an x squared line of best fit. Okay, I'll just capture this. There's my quadratic. And I can draw the thing as well. Alright, you just want to go underneath. Alright, may as well do the same thing for cubic and exponential. So here's my cubic one. Okay, so I'll copy this. And draw this one as well. And I better draw an exponential one as well. I think in your calculators you have two different options. I'd recommend choosing the one that doesn't have E on it. Alright, so there's my three models that I'm thinking of investigating. I'm not really sure which one of these I'm going to choose. Okay, so if I just look at these three models and sort of rank them in how well they fit the data, okay, I can look at their R-squared values. Okay, and I could rank them. The best one is cubic. Okay, then quadratic, then exponential. Okay, just based on these R-squared values from the calculator output. Okay, so that's one thing that we'd consider. Okay, these R-squared values. Okay, we could also just visually look at how well they seem to fit the data. The quadratic and the cubic, they look pretty good. Okay, whereas the exponential doesn't really seem to be fitting the data. Yeah, you get your 98.9% explanatory power, but especially at this higher end, we see it starting to increase at a rate a lot faster than the data is actually increasing. Okay, so we look at visual inspection. Quadratic and cubic are good. Okay, exponential deviates at higher speeds. Yeah, other things we can look at are what happens outside the stated domain. Okay, so if I look at, say, for example, the intercepts. So let's have a look at this quadratic. The intercept is 50. Okay, which means if you're going 0 miles per hour, it's going to take you 50 feet to stop. I don't think that makes much sense. Intercept here is 0.88, okay, which probably makes a lot more sense. You're going no speed, take you basically nothing to stop. Okay, and exponential is telling us it's going to take, so the A value is our intercept. It's going to take 22 meters to stop. Okay, so in terms of making sense of these intercepts, okay, the best one is cubic. Cubic, which is 0.88. Okay, then exponential of 22.3, and then quadratic 50.5. Okay, so there's a few things to think about with this data fitting. So look at the R-squared value, sure, see which one's higher, but also visually inspect the data. Does it make sense? Will it make sense for that trend to continue? Okay, and just looking at the intercepts as well, seeing if it makes sense slightly outside of the domain of your data. Remember, the domain of your data is these X values. Okay, we want to be able to explain what's happening within those X values, but also possibly be able to use the data to extrapolate outside of those domains. All right, so my choice would be the cubic model in this case. Okay, for those reasons. Okay, that has a good R-squared value. Visually seems to fit the data quite well. Okay, and the intercept seems to make sense as well. Okay, the equation is y equals, okay, essentially 0.0000524 x cubed plus 0.00992 x squared plus 1.63 x plus 0.88. That's just from the regression. If you did the regression on Excel, it would give you the equation directly. Okay, so reasonableness. Okay, this is where our model helps us out. Okay, it's reasonable for future predictions. As the y-intercept of 0.88 is reasonable for 0 miles per hour. Okay, in terms of strengths and weaknesses, so strengths, weaknesses is normally limitations. strengths, good R squared value, visual fit. Okay, and makes sense to continue. Okay, any weaknesses of this? Okay, it may not continue beyond x equals 80 at the same rate. Okay, so it's something for you to consider. You can go through this problem and you could easily justify choosing either the quadratic or the exponential for different reasons. Okay, but the big thing is having a look at the data, fitting a few different models, and then deciding on one of the models. So you won't need to do this for your assignment, okay, but it's a skill that you'll need for the future. Okay, to that end, there's a few problems here for you to have a go at doing some curve fitting yourself. Okay, first of all, thinking about what the pattern you'll expect to find, giving it a graph, and commenting on the reasonableness and the strengths limitations. So things like postage stamps, population of the Earth. Okay, don't use that data in your assignment. The pole vault heights and some biomass things and some questions to look at. Okay, so do these in